Hi everyone, welcome to the Chapter 16 Q&A. I'm going to go through the discussion board here and see if I can find some good questions to answer. Okay, so I got this question several times, first from Kayla, and she was asking, why are there many more ways to go a faster speed than a slower speed, as opposed to velocities, where a lower velocity is more probable than a higher velocity? Yeah, speed is different from that. And so I'm going to try to explain this, and it is quite a tricky and subtle issue. So imagine with me at first that there's a particle and it has a velocity in the x direction. And let's assume that just for the sake of the illustration, that it can only go velocities that are integer values, okay? So it can go in the positive direction or it can go in the negative direction. So it might have the velocity 0, at which case it falls in this little box right here. But if it has a velocity of 1, then we're going to say it falls in this box. If it has a velocity of 2, we'll say that it falls into this box. If the velocity is negative 1, it's in this box. And if it's negative 2, it's in this box. Notice that there is equal probability that it's in negative 1 or positive 1, or negative 2 or positive 2. There's equal probability. We can say the exact same thing about a particle that is moving in the y direction. So now we've got Vy going up or down, and it also can only take integer values, 0, negative 1, negative 2, positive 1, positive 2. So it can fall into this box, or this box, or this box, or this box, or this box. Okay? So that's considering just the velocities for now. But the speeds are different. So now let's consider the speeds. And I'm just going to begin with 2 dimensions, though the analogy definitely extends out to 3 dimensions. Okay, let's first consider the situation where Vx equals 0, Vy equals 0. What is the speed in this case? The speed is 0. And so which box does that fall into? That's going to fall into this box right here. All right, now let's consider the next situation. If Vx equaled 1, Vy equals 0, then that means the speed is going to equal 1. So which box is that? That would be this one right here. Because I didn't label these axes, but this is Vx going this way, and this is Vy going up this way. Now how about a different situation? What if Vx was negative 1 and Vy was 0? The speed would be 1. That's this box right here. And then next situation, Vx equals 0, Vy equals 1. Speed, again, equals 1. That's this little box right here. Now, Vx equals 0, Vy equals negative 1, V equals 1. Same speed. All of these red boxes have the same speed. And so what this is like is me taking an arrow with a speed of 1 and just finding all of the boxes that the arrow kind of passes through. And so the probability of the speed equaling 0 is 1/4 of the probability of the speed equaling 1. Now what if I choose a set of velocities that have a faster speed? So like what if the speed equaled 3? Well, that would be like me drawing an arrow out 1, 2, 3 tick marks to right there, and then making a circle that I could draw a speed of 3 on everywhere. Now, I would just have to draw all of the boxes that these arrows pass through. So as you can see, I've got a lot more of those boxes. I'm of course just approximating this right now, but hopefully you can kind of perceive how the probability of having a speed of 3 just occupies a lot more velocity boxes. And that's why higher speeds are more probable than lower speeds. And it's actually proportional to the surface area of a sphere. So the probability of having a particular speed is proportional to the surface area of a sphere of radius speed, whatever the speed we're talking about here. So Gabrielle asked this follow-up question. She asked, why is it impossible to have a speed of 0? And then later she asks, what role does temperature play in this? Well, the reason why it's impossible to have a speed of 0 just goes right back to this statement I made right here. The probability of a given speed is proportional to the surface area of a sphere of radius that speed. So if you have 0 speed, then the probability is the surface area of a sphere of radius 0, which is 0. And another way to think of that is just to consider this situation up here where I'm using infinitely small boxes. If the speed is non-zero, then you have infinitesimally small boxes, but you have a large number of them. And so that's how you're able to get some probability. But down at that tiny, tiny little central point, it's so infinitesimally small that it's impossible to get a speed of 0. And what role does T play? Well, remember the temperature is what gives us the Maxwell-Boltzmann distribution of velocities. So even though low speeds are less probable, high speeds are also less probable because the velocities are going to be limited by this bell curve of the temperature, remember? So it's going to be very improbable to get high velocity particles, and that proportionally creates a lower speed distribution. So that's why if we have the speed distribution here and then the probability of that speed, it starts at 0 and then it goes up, but then kind of tapers off and falls off just like that velocity bell curve. So that's the role that temperature plays. Okay, the next question was asked by Alyssa, where she said, how did they come up with the symbol Z11 for the particle collision frequency? It seems kind of random for it to be the letter Z with 2 1s or an 11. Well, I don't know why they came up with Z. Your guess is as good as mine, how they choose the symbols for these things. It's probably just whoever wrote it down first chooses a random symbol. But the reason for 1, 1 is that if we've got a mixture of gases, like, I don't know, N2 and O2, then we might call N2, gas 1 or particle 1, and we might call O2 gas 2 or particle 2. And what I didn't tell you about is if you have a collisional frequency, it's going to be different whether for a given particle it's N2 colliding with another N2 or N2 colliding with an O2 or O2 colliding with another O2. So Z11 implies that it's N2 colliding with another N2. If we had said Z12, then that would be N2 colliding with O2. And so that's what those little indices mean down there. Okay, the next question that I really got quite often are, what are the differences between the most probable speed, the average speed, and the root mean square speed? If you don't know about their mathematical differences, I would encourage you to review the video from day 2 of videos from day 2 of chapter 16, where I actually outlined their mathematical differences. But a lot of people are also asking about what are their practical applications. And I know of a few practical applications, though this is by no means an exhaustive list. One thing that I mentioned in those videos is that this root mean square speed is related to the speed of sound. So if we have the speed of sound in a gas, that is going to be equal to the root mean squared speed of the gas particles in there. So maybe you need to calculate the speed of sound in a particular gas. Well, now you can do it because you know the formula. So that would be an example of a practical application of that. How about practical applications of the average speed? Well, we saw how the average speed is related to the mean free path, and how it's also to effusion. So each of these just appear in different physical locations that it just provides another connection that you can use to calculate the value that you need. So hopefully this is a couple of useful practical applications of these quantities.